Hi everyone. Thank you all so much for joining us today, and we'll be kicking it off. So the first presentation is about the project titled "Heating Loads in Alaska and Beyond," and I'd like to start off by introducing the team. We've got our team lead Erin, our data scientist Nick, and from left to right the fellows myself, Philippe, Maddie, Shamsi, and Vidisha. We have affiliations with a number of institutions, including the University of Washington, the University of Alaska, Stanford University, and Carnegie Mellon University, and bring subject expertise in areas such as economics, engineering, public health, machine learning, and regional Alaska expertise. For context, global warming is the most pressing challenge of our generation. It is happening approximately 4 times faster in Alaska when compared to the global average. There's a huge and increasing urgency to decarbonize energy sources, particularly in Alaska. And in order to reduce the accelerating impacts of climate change, reductions in emissions are vital. And therefore, national and local decarbonization is critical. Our work initially focuses on Alaska's rail belt region. The rail belt electrical grid region is defined as the service area of 6 regulated public utilities that extend from Fairbanks to Anchorage and the Kenai Peninsula. Residential and commercial heating make up large parts of the contribution toward global warming, and a large aspect of reducing energy and heating use is first understanding the current state, and thus this project aims to drastically improve the way heating loads are estimated in Alaska. Alaska has unique needs and challenges relative to the rest of the United States. For example, Alaska has far less centralized energy, a large culture of independence, and much colder temperature in general. And so the lack of centralized energy information is a key reason for this project in the first place. And so therefore, we aim to fill this energy use data gap in order to better understand the current state of energy and heating needs in Alaska. We do so by taking a geospatially informed approach. This means we use large-scale satellite data to get information with high granularity. In preparation and during this project, we have met with various Alaska-based researchers and experts to gain a better understanding of the current state of energy needs in Alaska. We've had individual meetings with researchers from national renewable energy laboratories. We met with scientists and Alaska heating experts, and we also had group meetings with experts from the University of Alaska and other parts of Alaska who are very well versed in the current literature and scholarship. Our work is in contrast to that current scholarship and research being done, particularly in this region. At the moment, micro-level approaches, meaning very time-intensive, on-the-ground approaches, are the only ones yielding results. So this means researchers go to individual houses, take measurements, install meters, and wait for months for results. In contrast, our top-down large-scale approach allows us to estimate the heating needs for large parts of Alaska. This work has immediate impact since it will enable researchers to do large-scale calculations for all of Alaska, which is previously not been possible. Additionally, results can be used for immediate sustainability and decarbonization policy implementations. And lastly, this approach can be expanded to the greater Arctic region, which shares similar challenges. So our task was to create a model that predicts heating loads for buildings, whether that be commercial or residential, in Alaska, accounting for very local climate. And we start off by doing a focus on the rail belt.
So what are heating loads? For our project, we define heating loads as BTUs per year and alternatively as BTUs per year per square foot. And a BTU, because many aren't familiar with that unit, it's a British thermal unit, and one of them is roughly equivalent to the energy released when you burn a match. And for reference, a heating load for a 1,500 square foot building can range between 45 and 90,000 BTUs per year. So that example I gave, there was a range of heating load, and that's because there are a lot of things that contribute to how much heat it takes to heat a given space. So for the purposes of our project, we went with these 4 variables that we would need to be able to estimate heating load. So the first is local climate conditions. This is pretty intuitive. If it's warmer out, there's less energy needed to heat your home. And we also needed the height, the base area, and the age of a building. What you'll notice about all 4 of these is that we can approach them geospatially. So that lets us use that large scale approach that Philippe described. A very broad flow chart of the process we're embarking on. First, we take building features, that's the building age, height, and footprint. We add to it climate features that we generate out of many years of climate data, combine them into a sort of model, and the output from that model will be heating load in the form of BTUs. To go a little bit deeper into the work, we're actually using a supervised learning model. So supervised learning needs output data to train on. Here, that's heating loads. And as Philippe described, there is no ground truth estimate for heating because that work is very, very challenging and we don't have it for large regions. What we do have are current estimates from researchers that have created regression equations for both Anchorage and Fairbanks to give some sort of continuous BTU estimate for buildings in those cities. So how does our model learn? So what we do is capitalize on the climate differences between those 2 cities, which as you can see are in different regions of Alaska. And then we generalize to the rail belt that has all sorts of different climate variation.
The extraction of building features from geospatial data was one of the biggest and most challenging aspects of our project. For this, we used Google Earth Engine, which is a cloud computing platform that allows one to access and analyze geospatial big data. The public data sets we used from Google Earth Engine's archive consisted of satellite images captured across time, as well as geometries of building outlines in Alaska. We had to aggregate these data, both temporally and spatially, to arrive at building level features and then export these as tabular data for analysis. The next slides describe this process further. A key advantage of using geospatial data is that it not only allows us to identify where buildings are, but also estimate their ages and dimensions. A building's age or year of build may be important for estimating heating needs, as it may be correlated with air leakage. We estimate a building's age using data that tracked changes in land vegetation since 1985. Similarly, a building's height and base area determine its volume and thus may affect the amount of energy required to heat a building. While building heights were calculated using land elevation data, areas of building bases were estimated from building outlines. The shapes shown in orange in the map on the right are examples of building outlines we used. An important aspect of our model is that it uses local climate variables to predict heating needs of a building. The climate around a building is likely to influence its heating needs, and local climate may vary significantly within a state. By mapping land surface temperature data over building outlines and aggregating them over time, we construct heating and cooling degree days for each building. Degree days are simply measures of how cold or warm a location is. The more extreme the outside temperature, the higher the number of degree days, resulting in higher levels of energy use for space heating or cooling. The map that you see on this slide is a zoomed in version of the annual heating degree days mapped over Alaska. The variation in colors on the map correspond to the variation in local climate observed in the state. Pink denotes higher absolute value of heating degree days, that is, areas which need more heating. While climate is subject to cyclic fluctuations over time, the climate pattern observed in the recent decade may differ significantly from earlier ones due to climate change. Therefore, it is hard to say if more recent climate data or longer run climate variables would be better predictors of heating needs. As a result, using data from 1981 to 2020, we created 10-year as well as 30-year averages of degree days, which go as inputs into our model. with data on building features, climate, as well as simulated data on heating loads, we try to estimate a model that can predict heating loads at the building level. We explored a range of models, which include ordinary least squares, linear regression, ridge regressions, with and without polynomial features, decision trees, and random forests. We evaluated these models using their mean squared error on the test data. Each model's mean squared error is listed on this table, and one can see that it keeps reducing from top to bottom, showing that the random forest regression performs the best. A point to note here is that we are yet to explore a wide range of models and intend to do so as we get access to a more comprehensive heating loads database. On this slide, we try to explore which features are actually important in predicting heating loads as a part of the random forest that fitted our data the best. The y-axis shows various features which were included in the model, and the x-axis shows their importance on a logarithmic scale. Feature importance can be described as a score assigned to features based on how significant they are at predicting a target variable. From the graph, age seems to be the most important predictor. This can be expected as older buildings might be less energy efficient and more prone to air leakage. However, this may also be due to the output we used for model training, as it was interpolated from regressions of heating loads on age. We also see that heating degree days averaged over 1981 to 2010 and 1991 to 2000 are relevant in predicting heating needs. This highlights that it may be important to take both recent and older climate data into account while estimating heating needs. While these results are a part of a proof of concept exercise, they do have the potential to inform decarbonization policies like energy retrofitting in Alaska. For instance, the importance of the age variable as a predictor may answer if it is better to replace old buildings rather than retrofit them to save energy.
As Vidisha has shown in the last slide, we see that age and location-based climate data are the features that are most informing our models. As such, it's important to ask the question, what happens when we change how we're sampling these features? The basic idea behind data sampling is to balance the data that you're working with across a number of different factors. And the motivation behind this is to avoid biasing your model towards particular types of data. For example, in this project, we explored balancing our data over location and over building age. What this means is, for example, Anchorage and Fairbanks. Anchorage has a higher population than Fairbanks. As such, there are more buildings located in Anchorage than there are in Fairbanks. So without balancing our location-based data, our model is receiving more input on heating load needs in Anchorage than it is in Fairbanks. So to balance these, we upsample Fairbanks to make sure that the buildings coming from Fairbanks and the buildings coming from Anchorage are the same amount, so our model is not being weighted in any particular way towards location. From doing these results, we can compare what balancing location and balancing age and how that affected our different models. As we can see, balancing location improved the models, specifically the decision tree model and the random forest model, giving a much lower mean squared error for both of those models. And balancing across age, so making sure that we're passing an even distribution of building ages to the model, improved all of the different regression models. So we can see from this that balancing the data is definitely an important factor and can improve the heating load estimates that we're outputting. During this project, we have generated heating load estimates using our model that capture the variation in local climate. In addition to generating these estimations using past and current climate estimates, we also predicted heating needs for future climate estimates. All of this work is filling a vital information gap in the field of heating and decarbonization in Alaska, and can now be used to inform relevant policies and inform the way towards decarbonization in Alaska. Throughout this project, we've faced challenges, including challenges regarding the data and ethical challenges. For data challenges, the Arctic region specifically has particular challenges associated with collecting data there due to like specific regional weather patterns and things like that that make it a unique area. As a result, our team has had to overcome this issue, and our solution was to take into account multiple different data sources for the data that we needed for our model to combat the fact that many of the data sets we were looking at were sparse in certain regions. In addition, we also encountered some data-related challenges while using Google Earth Engine. While Google Earth Engine is a great tool for large-scale geospatial analysis, the number of buildings and building features that we were looking at in this project is particularly large. We were looking at over 100,000 buildings and approximately 10 features per building that were quite detailed. As a result, we faced some challenges when trying to export the data from Google Earth Engine to pass it over to our model. The solution to this was to optimize the way in which we were exporting our data. Some of the ethical challenges that we faced on this project include the fact that we're working with large-scale geospatial data that's open source. Due to the open source nature of this data, it is impossible to collect any sort of community consent about the information in the data. And so as such, as researchers in this field, we need to make sure to tread carefully and be transparent about how we're using this data. In addition, our top-down geospatial approach required assumptions as we went along. For example, our model assumes that the heat needed for the third floor of a building is the same as the heat needed for the first floor, which is most likely not true considering that heat rises and the third floor probably wouldn't need as much heating as the first floor. However, this was a simplifying assumption that we had to make in order to complete this project. These kinds of assumptions all require transparency on our part as researchers. While this project was only 10 weeks, its work is very important, and several of us will be continuing on the project. As such, we have a number of different tasks we'd like to see completed in the field. First off, we would like to incorporate the retrofit database that Vidisha talked about earlier. We think that incorporating this database into our model could tell us more about how effective retrofitting really is, and it could possibly affect how important the building age variable is that we saw in our feature importance analysis. In addition, we want to add more climate simulation models into our model, particularly those with higher spatial resolution, which will give us more accuracy and tell us a little bit more about the differences in weather between all of the different areas in Alaska. In addition, we did not have a chance to do a full sensitivity exploration of our models, meaning we didn't get to explore, for example, the assumption I stated earlier about building stories needing the same amount of heat. Finally, when talking to researchers about what they wanted to see come out of this project, one of the specific things that was noted was hourly heating load estimates. This is definitely possible to do from the information that we've gathered on this project and would not be too challenging, but it's a next step that we'd like to take in order to continue our relationship and collaboration with relevant researchers. Finally, other Arctic regions and the rest of Alaska can benefit from this work as well. It's very relevant and clearly important, as Philippe said, since global warming is one of the biggest problems of our generation. At this time, we'd like to thank our supporters of this project, the University of Washington, specifically the eScience Institute and the Data Science for Social Good program, and Micron. We'd like to thank all the attendees today for coming to hear about our project. We really enjoyed working on it this summer.